In this presentation, I want to provide you an overview of Project 4.1 Puzzle Design Challenge. This will cover everything from the very first thing we do on this project all the way to the very last thing we do on this project. So please make sure you follow all the way through so you'll know exactly what's expected of you and what you need to produce for this project. First, we're going to look at the Project 4.1 Puzzle Design Challenge requirements. We need to study the Project 4.1 Puzzle Design Challenge design brief. I'm going to quickly go through this. The client is, this is a hypothetical scenario here. So the client is a Fine Office Furniture Incorporated. The target consumer is ages 3 and up. So you're designing a puzzle for young people who are ages 3 and up. A local office furniture manufacturing company throws away tens of thousands of scrapped 3/4 inch hardwood cubes that result from its furniture construction processes. The material is expensive and the scrap represents a sizable loss of profit. So that's the problem statement. So this company's making furniture out of wood, obviously, and they have a lot of wood left over and they feel like that's a huge loss for their company. So here's the design statement. Fine Office Furniture Incorporated would like to return value to its waste product by using it as the raw material for the desktop novelty items that will be sold on the showroom floor. Design, build, test, document, and present a three-dimensional puzzle system that is made from the scrap hardwood cubes. The puzzle system must provide an appropriate degree of challenge to a person who is 3 years of age or older. So here are your constraints, and this is what the rules that you have to follow as you design and make this project. First of all, the puzzle must be fabricated from 27 3/4 inch hardwood cubes. Okay, you will be provided with 27 3/4 inch hardwood cubes. The puzzle system must contain exactly 5 pieces. So you will take your 27 3/4 inch hardwood cubes and you will put them together in random different shapes to make 5 different puzzle pieces that when assembled together will make the final puzzle. You'll see an example of this later in this presentation. Each individual puzzle piece must consist of at least 4 but no more than 6 hardwood cubes that are permanently attached to each other. Number 4, no 2 puzzle pieces can be the same. Number 5, the 5 puzzle pieces must assemble to form a 2 1/4 inch cube. Again, you will see an example of what that looks like. 6, some puzzle pieces or some puzzle parts should interlock. That'll ensure that when you hold the puzzle pieces, it's just not going to fall apart. So they should interlock. And number 7, no puzzle piece can be a 4-block or 6-block wall. So here's an example of a 4-block wall, the orange piece there. You cannot have a piece that is a 4-block wall that looks like what's on the screen, and you cannot have a piece that is a 6-block wall, as you'll see in the blue piece in the bottom of this slide here. So let's look at the brainstorming and sketching part of this project. You will need isometric graph paper to generate various different puzzle part combinations. This will connect directly with activity 4.1a, brainstorming possible combinations. You'll put your sketches in your engineering notebook and you will definitely need to submit these in Schoology, but this is a part of the project as well. So this is activity 4.1a, brainstorming possible combinations for different shapes. It's really just an exercise to try to get your brain to see different types of possibilities that exist from as little as 3 cubes all the way up to 6 cubes. So this is just an example, and I will provide more detail about this activity in another video. So here's a continuation of the 5 cube combinations and 6 cube combinations. So with the assistance of linking cubes, you're going to develop 2 possible solutions. You're going to neatly sketch and color code your 5 parts for each solution. So you're making 2 solutions and you need to color code both of these solutions so you can document the solutions you've come up with. You need to document how they fit together and how to create the puzzle. So you're going to be coming up with different pieces that are assembled together to make this puzzle cube. And so you need to put your two possible solutions in your engineering notebook so you can document how it's solved, how the pieces are created, and how the puzzle is put together so that you can create this in CAD and you can actually fabricate it yourself. So here's an example of what I did. So I'm going to give you a piece of paper. As you'll see on the left side of this screen, you'll see an assembled cube. That is what the cube will look like when it's all assembled together. And then you'll see that there is a top half, there is a middle half, and there is a bottom half. So I shouldn't say halves, it should be a third. So this is top, middle, and bottom. And so these three levels represent this puzzle over here. These right here are the individual pieces that are assembled over here. So for example, you'll see the yellow piece right here. That is where the yellow piece goes in this cube. So not only is this a solution or a way that I documented how this puzzle piece or this puzzle is solved, but I also have a sketch of the different pieces here, and they're color coded and they are sketched as isometrics. Here's my solution number 2. Same thought process. The different levels here represent this assembled cube here, and on the right side I have the isometric shapes that I will make in CAD. These are solid shapes. When all assembled together the correct way, it will generate this puzzle piece right here in the center. So with the use of a decision matrix, we need to decide what is the best solution to make. So the decision matrix will really help you decide which one you should make from this point forward. You are not making two puzzle cubes, you're only making one, but you have to come up with two possible solutions, and then you will decide which one you will make in CAD and which one you will fabricate. So this is an example. This is my decision matrix for my project. So solution number 1, and the different columns here, 5 pieces, 4 to 6 pieces, different, interlock, difficult, they represent the different constraints that you have to follow for this project. So think of these like questions. So for solution number 1, do I have 5 pieces? Yes or no? If it is a yes, I scored it a 2. If it was a no, I gave it a 1. Are each of my pieces made up of 4 to 6 3/4 inch hardwood cubes? Yes or no? Is each piece different? They cannot be alike. Are they different? Yes. Do they interlock? I had some that did not really interlock very well, so I scored that lower. And then, is it difficult? I scored solution number 1 lower than my second one. So you'll see that my second solution won on this scoring decision matrix. And if you end up having a tie where you have 10-10, then you decide which one is harder, which one has better interlocking pieces, and then you just score the one that doesn't meet those requirements, or at least on a lesser level, you just score that one with lower points. So next you're going to sketch the multi-views of each of your 5 puzzle pieces from the solution that you have are going to make. So here's the multi-views for the pieces that I made. And so yours will need to look like this as the top, front, and right side view of these 5 pieces from my solution number 2. Then we're going to actually make each of these pieces in Inventor. For those of you who do not have Inventor, you will use OnShape. And so you will make all 5 of these pieces as solid pieces in CAD, whether it be Inventor or whether it be OnShape. You will not only make these pieces, but you will make an assembly of these pieces, you will make an explosion of these pieces, and you will put these pieces on sheets so that they can be printed out and possibly manufactured in the future. They won't really be manufactured. You'll be the only person who will make this cube, but if we were to send this off to a manufacturer, they could use your drawings to recreate your pieces. So here's an example of what the pieces look like in Inventor. So each of these pieces are made individually in separate files. Then we have an assembly. Each of those separate 5 files in Inventor for each of those 5 pieces are brought into one file, and then they are assembled together as seen on the screen. Then we make an explosion drawing from that assembly. Again, this is a separate file, and we will take the assembly, add it into this file, and then we will explode it in a very organized way. And then the last step is to make the multi-view. So we'll have a cover page. We're going to have a multi-view for each of the 5 pieces. And then we will have an explosion drawing with each part with a balloon, which will have a number in it. And then we will have a parts list. And then we will have a solution drawing. So this, anybody can take this, look at how to hold the green piece for step number 1. Then they'll know how to add the yellow piece, then the red piece, then the black piece, and then the blue piece, and then they will have a solution for this project. The final part of this project is the fabrication of your 5 parts with the 27 wooden cubes that you've been given. You'll use glue and markers to fabricate your 5 puzzle pieces. So here's my assembled, glued together and colored puzzle for my solution number 2. Notice that the blue pieces are glued together and then I colored it blue. You want to be able to let people play this. I've had students in the past who will make the red, the blue, the green, the yellow, and black. They'll make them, it'll look great, but for some reason they glue all the pieces together and nobody can even play it. The purpose of this is to make 5 individual pieces that are different colors that you could lay out on a table and tell someone to solve it. So this is the 3 different big parts. So there's the sketching part, there's the CAD part, and then there's the fabrication part of this project.